Hello, I am Abhishek Tiwari and today we are going to learn about projectile motion. This is motion in two dimensions. So to begin with projectile motion, I would like to ask you a simple question. I know we would have played throwing the ball and trying to catch the ball. And every time we would have gauged or tried to understand what would be the projection or the trajectory of the ball so as to particularly catch it. Well, apart from this, this phenomena is also used whenever soldiers use tanks or whenever a plane is flying and it tries to throw a particular missile into the projections. So, to understand this particular idea, I would like to show you a simple demonstration on what is called a projectile motion. If you could look forward on my screen, as you can see, this is a simple explanation of the projectile motion. This is a simple tank, a tank that is going to throw a projectile. When a tank is throwing a projectile horizontally, this is what is the projection. When the same tank is trying to throw it vertically, this is motion in another one dimension, but along the horizontal line, it goes and it comes back straight in. But when the same is thrown with this kind of an angle, this kind of a projection is called an oblique projection. This comprises of motion in one dimension, motion in two dimension, and motion in three dimensions. So in this case, we are going to have just the motion in two dimensions. As you can see that the velocity vectors or the components of the vectors are displayed over here. As you see, the ball goes in and it hits the particular thing down. Now what I am throwing is a pumpkin. And what you are seeing is this is the exact place where the projectile is dropping off. So to understand the idea of what is called a projection, I would like to tell you about three things. Each projectile motion comprised of three basic things. The first one is at the origin. When we talk about the time period of the projectile, the height from which it is projected, and the maximum height of the projectile. And number two, we are talking about the maximum height of the projectile. Number three, we are talking about the range of the projectile. So a range is indicative of what is the exact distance the projectile has covered from its starting positions. We are going to do first the understanding of what are the different categories of these kinds of projections and what are the formula to have these kinds of categories. The second, we are going to see what are the derivations of these kinds of projections. And the third thing in today's lesson that we're going to see is what are the different kinds of questions that will be asked for our questions, for our exams. So if you can look forward in my screen. And now, some basic keys and fundamental. If you can look on the board, I have drawn a particular projectile motion. In this motion, as you can see, if I am at point O and I throw the ball from point O, then this ball is going to follow a path from O to P, P to A to Q, and Q to B. During this motion is considered as a free fall motion. That is because when you are throwing a projection, it is always under the influence of gravity. There is no horizontal acceleration whatsoever under any circumstance. And that is the reason why this motion is called, also known as motion under free fall. Now, as the object goes up, you can see that there are two components of velocity, one over here along x-axis and one over here along y-axis. The velocity along y-axis slowly reduces until and unless the projectile reaches to a maximum height h. Once it reaches to the maximum height h, since it is under the influence of gravity, the vertical projection, the vertical component of the velocity slowly becomes zero and then it moves in the opposite direction. And that's the reason why you can always find that this particular component, this particular idea of moving is when the ball is moving or any projection is moving, it is moving under the influence of free fall. Now, to understand this, let us consider two particular things. First is along horizontal motion. As you can see, along horizontal motion, the component of the velocity is considered to be ux, which is u cos theta, and along vertical is considered to be uy, which is u sin theta. And the acceleration along the horizontal is always zero, and along the vertical it is considered to be g. The sign convention can be taken as minus g because we are always moving against, first we are moving against the motion of gravity and next we are moving towards. So first we'll consider it as minus g. Now, applying the sign convention can be taking place later. The first thing that we need to do is we need to find out what is the absolute time of projection. Let us consider that A is the maximum height of the projectile. As soon as it reaches point A, the velocity along the x-axis completely determines its speed at point A. The velocity along y-axis will slowly reduce and become equal to 0. Now, this can be proven by a very simple fact. Now, if you can see my screen, I'm going to slowly project a small object. Let us say I'm going to project a cannonball or a tank shell. And then we are going to see how this particular velocity component is going to change later on. So the velocity component is determined by a green symbol, and slowly if you are able to see it, you will be able to see how the ball is projected at an angle of 45 degrees from the ground with an initial speed of 15 meters per second. So as you see that the component of the velocity is slowly reducing. It has come to a point where the component of the velocity along the y-axis have slowly come out to be zero. Now, as you check carefully, the component of the velocity is increasing along the y-axis, but in the negative direction. That's because first the projectile was moving against the gravity. So I was pushing it, but the gravity was pulling it down, and hence the velocity was decreasing. This is retardation. And slowly, when it reaches the highest point, when it moves forward down, you can see that this particular component is increasing. But if you look carefully, there is no change along the x component of the velocity vector. That clearly determines that a projectile just changes velocity along y because it has acceleration only along y-axis and no acceleration whatsoever along the y-axis. Now, if you can, along the x-axis. So, if you look carefully at this particular diagram, check this out. I have only acceleration along y-axis, but no acceleration along x-axis whatsoever. This is what is termed as projectile motion. Now let's come back to the original screen to see what is happening. So in our original derivation, let us try to find out what is really happening. Yeah, let's begin. So we are going to first find out what would be the time period of our projectile motion. So I am considering that I am at point A. So if I am at point A, I know that the velocity of the y component is 0 using the equations of motion, one of the equation of motion which states that the final velocity is equal to the sum of initial velocity and the product of the acceleration and time period. Now, if I can see that at point A, the time period of the projectile is exactly half of what it's going to do in the beginning and what it's going to do at the ending. So exactly half, I'm considering that the total time period of the projectile is determined and represented by capital T. So at point A, I can say that the time period will be equal to T by 2. Let us consider Vy equal to 0 at point A, and Uy is the initial velocity, which is the component of the initial projection, which I'm projecting the speed, adding it to Ay, which is minus g because the projectile was moving against the gravity, and this as the total time divided by half. Total time t is the time period of the exact projectile motion. So I can imply over here that T will be equal to 2u sine theta over G, which will be the exact formula for the time period of the projectile, any projectile, be it of any projection, the total time period will always be with this represented by this formula. Now, let us move forward to understand what would be the next things. So the second thing that we are going to find out would be the maximum height of the projection. The maximum height is represented by the length MA and represented by the letter H. Capital H is going to be deriving you or giving you the maximum height of the projection. Now, a simple question, if you would understand, is whenever you play, whenever you throw a ball to someone, if you throw a ball with a small angle, the ball will go straight forward for a longer distance. But whenever you throw it at a higher angle, the ball is going to go more high. So if you understand carefully, if you understand the idea, I will show you how. Whenever the height of a projectile is considered, we always consider an angle to represent that particular height. So to understand the maximum height of the projection, I'm going to consider same point A. And at point A, I can simply say that the maximum height H will be equal to, S is equal to ut plus half at square. That's the second equation of motion. In this case, since we are talking about the y-axis, we are going to take everything along the y-axis. So H will be equal to uy into the time period t plus half into the acceleration along y-axis and t square. In this case as well, I am considering at point A everything. So at point A, the time period will be t by 2 and I will have the acceleration as negative. So I have uy equals u sine theta plus half ay is minus g times t square. So this is into t and this will be equal to to by 2 the whole square. Now, considering the same idea, let's consider small t equal to t by 2 in both the cases because the time period is half of the exact time period of the projectile. I will have h equals u sine theta multiplied by small t, which is equal to t by 2. And t by 2 from equation number 1 can be taken as u sine theta over g, because the 2 is going to come to the denominator, and then I'll minus it with g over 2 and I'll again get u square sine square theta over g square. If you subtract the formula, you will find that both of them can be subtracted. One is 1 and the other is half. So I'll get the answer as u square sine square theta over 2g. Now this is going to be the exact formula for finding out what would be the maximum height of any projectile that is shown by this kind of a projection. Now, understand this idea, guys. We are talking about the exact projectile anyways which with it is moving. So irrespective of how you are considering it, we will still have this particular thing taken into consideration. Now, try to understand the last thing that we are going to see in this case is the range. So the range of the projectile is actually the maximum horizontal distance that a projectile is covering. That is called the maximum range of the projection. Now, if you consider the maximum range of the projection, then in this case, if you look carefully, we are talking about simply as I can say that the maximum distance OB. Now, look carefully. OB is the maximum distance along x-axis. Along x-axis, let us say the distance is represented by capital R. That's the formula for range. Since it is a horizontal distance, I will take horizontal speed multiplied by the total time period of the projectile plus half into the maximum, what is the horizontal acceleration, and t square. Now, since the acceleration along x-axis is equal to 0, I can simply write it as u cos theta times, and the formula for t is 2u sine theta over g. So if I reduce this formula using trigonometry, I'll get this as u square sine 2 theta over g. So guys, these are the three basic formulas that will be used anytime, anywhere, whenever we are talking about these kinds of projections, or whenever we are talking about projectile motion and projections. One is for the time period, the maximum height it can cover, and the third formula is the amount of range it covers. But let us assume that I am somewhere at point P. And at point P, this is just an assumption. Let us simply assume that at point P, I have my coordinates as x and y. So at point P, I am assuming that my coordinates are simply x and y, where x is the horizontal distance and y is the vertical distance. How would I find out what would be the equation of this entire trajectory and what is the projectile going to move? So this is a real life application that is used by various tanks, the soldiers, the people in the army, the people in the air force, and is also used in a lot of physics applications, such as projecting neutrons or electrons, okay, when they do not follow a certain path. So this is what is called the equation of trajectory, mostly used in space. To understand the equation of trajectory, I need to understand what is it exactly. It is the exact path followed by the projectile during its entire course of motion before it comes down to rest. So at P, I can say that, let's assume that the horizontal distance is x. So since there is no acceleration, I can say that x is equal to the velocity along x-axis times the time period. Since I do not know that at point P, what is the time period, I'm trying to find out what is the time period. I can say that x equals u cos theta times the time period at point T. This can also be concluded as T equals x over u cos theta. Now, I'm assuming that this is my time period at the position or at the point P during the entire projectile motion. Now, to find out what would be the exact equation of the trajectory, I need to find out what would be the y-axis or the y-coordinate for this. So I'm going to put in the equation y equals uyt plus half ayt square. So if I put the value of y, this is u sine theta, multiplied by the time period, which is x over u cos theta, plus half ay is equal to minus g, and the t square will be x over u cos theta, the whole square. So I can have y, the exact equation as y equals x tan theta minus g x square divided by 2u square, and the cos square theta at the denominator by using trigonometry can be converted to sec square theta. So my dear friends, this will be the exact equation of the projectile motion while it is following its own trajectory. Using this equation, you can find out where the projectile is going to land at any point of time by just understanding the initial velocity, the points in which you're following, the coordinates of the point, and just the angle of the projection. I hope this much is clear to everyone, guys. What I'm going to do is you can take a screenshot of this and keep it with you at all times just to understand from where these formulas have come. And now we're going to see two questions based on the previous years to understand what is the exact idea and where are the things with that we are going to use this particular projectile motion. So in a simple question, it was given that the velocity of a projectile motion was v equals I cap plus 2j cap meters per second, where the acceleration due to gravity was 10 meters per second square. And what we need to find was to find out what is the equation of projection. So as you can see, there will be four options given to you. All the options would be either similar or there would be some things that would be different. Now, To understand about the equation of projection, you must remember that the equation of projection that we have previously derived was y equals x tan theta minus, excuse me, x square 2u sec square theta. Now, from this, what we can find out? If you look at the question, this question was asked in one of the previous year's questions in JEEs. So it's a simple case of idea. You must understand that the velocity is divided into two components. In this case, it is given in the vector formula. So we need to identify what would be the vector thing. So let's find out what would be the angle. So the value of tan theta will be equal to the component of the velocity along y-axis divided by the component along x-axis, which is equal to 2 over 1, which will be equal to 2. Next, this will give me the value of tan theta. That is what I have right now. Since I do not know the x and the y coordinates, I don't need to do anything. To find out the value of u, we must find out what will be the value of the magnitude of this vector. To find out the magnitude of the vector v, I will have to use the vectors. You know how to use vectors. So it's simple. I will take the square root of both the x components and the y components, which will be equal to root over 5 meters per second. That will be the magnitude of the vector. Hence, I also have the value of u with me. And to find the value of sec square theta, you must know a bit of trigonometry. If you can remember the formula, it's an which says that 1 plus tan square theta will be equal to sec square theta. So again, using the same formula, I can use that 1 plus tan square theta will be the value of 2 the square, which is equal to 1 plus 4, which is close to 5. So what I'm trying to do is I'm just trying to take out the variables. Now I have all the variables and all the values of the variables. I'm just going to put it in the equation of the projectile that we have derived earlier, which was not difficult. So I have my equation as y equals x into tan theta, which is 2 minus 10 times x square over 2 times u will be close to 5. U will be close to root over 5, and I will multiply it by sec squared theta, which is also equal to 5. But if you look carefully in this formula, this should be u squared. So I will have to square this, and I have y equals 2x minus 5x squared, because I'll cancel both of them together. And this is, my dear friends, the equation of the projectile motion. And as you can see that it will hardly take me less than 30 seconds to complete this question, which was asked apparently in one of the previous year papers. And you see, projectile motion is not that much difficult. It's an easy topic and can be done easily, provided you understand the exact idea of the motion. Now, moving forward with the next question. So let's see what's the next question is. So the next question is this. This was asked in 2019 on 10th of Jan in the morning. Sorry, 9th of Jan in the evening paper. It states that you have two guns A and B that can fire bullets at speeds 1 kilometer per second and 2 kilometer per second. So you see you have two guns, different speeds is the muzzle speed, the muzzle velocity. So from a point on the horizontal ground, they are fired in all possible directions. So the bullets are fired in a round circle, so they're possibly fired in all directions. We need to find out what would be the ratio of the maximum areas covered. So this is one of the questions that was asked in the year 2019. Now we're going to see how we can solve this question. So let's go back to our whiteboard. So like I said, we have two guns that are firing bullets. Let's say we have gun 1, which is firing bullet at a speed of 1 kilometer per second, and then you have the gun 2, which is firing the bullet at 2 kilometers per second. And we need to find out what would be the ratio of the ranges that is going to cover, or we need to find out the maximum areas it can cover properly. Now, to understand the maximum area it can cover, let us understand that if a gun is firing a projection like this, then the entire range covered by, or the maximum range covered would be the ranges that is covered in all directions. So this would be the circle of influence of the entire area. I'm sorry, my drawing is horrible. So please bear with it. Now let's try to understand what exactly it means by this. I will say that the first gun is going to cover range R1 in one area, in one direction. And the gun 2 is going to cover range R2 in one direction, that is, let's say, in forward X direction. So if I'm taking about a circle, then I will have gun 1 or gun 2 covering an area. The entire area covered by it will be equal to pi times R1 square. And for A2, that will be equal to pi times R2 square. If you look carefully, guys, the formula for range is u square sine 2 theta over g. It is dependent on the angle, dependent on g, dependent on the initial velocity. The thing is, neither the angle nor the acceleration due to gravity is changing in both the sequences. So I can say that R is directly proportional to u square, and the square of R will be proportional to u times the power 4. So if I want to find out the exact area covered, I just need to take out the ratio of the initial velocity and raise it to power 4. So the answer will be equal to 1 over 16, and my answer will be close to 1 over 16. So if you look carefully, guys, I did not even do anything. This is like a very simple question. This was asked in 2019 in the second term. Second time zone. We have two periods, right? In the morning and the evening. So this was asked in the evening. So I guess that is all about the beginning of the projectile motion. More to come, and we'll see what we can do after that. All right. Thank you. And